Hi, this is Olivia Stodig, and today I'll be talking about working with spreadsheets. That's specifically using our new Dapta web app, which I'll introduce in a moment. To find out more about the web app, you can visit our website, and you can even try it out for free by just clicking this button here, which will then give you access to the dashboard button at the top right. So today the topic is working with spreadsheets. The first question we might want to ask is, why do we actually use spreadsheets? And then once we've covered that, I'll introduce a quick example. That's the paraboloid spreadsheet. And we'll use that within the Dapta web app to create a component, automate the execution of that component, and then look at the inputs and outputs. So stay tuned. So why do we use spreadsheets? The first reason is that spreadsheets are really easy to access for almost everyone. You've probably got a software that runs spreadsheets at home and on your work computer as well. Typically, that will be Microsoft Excel, but there's obviously a lot of other options available these days as well, such as Google Sheets and also LibreOffice, which I'll be using in this demo. It's also a very versatile tool. It allows you to store, visualize, and compute data. In the most basic form, you can actually point and click and enter data manually, but it can also be very powerful when you know how to use macros. Finally, because of these first two reasons, there's a lot of legacy tools, especially in industry, that are built around spreadsheets. So sometimes you just have no choice. So let's go on to an example. Okay, so I've just opened our spreadsheet, the paraboloid.ods in LibreOffice Calc. This is what it looks like. It should be fairly similar if you open this another tool. You will need to allow macros to be able to see these plots and to be able to generate those fxy outputs here. That's because we're actually using a function that's evaluated through a macro. So the inputs are x and y values, and fxy is a smooth paraboloid function of x and y that has a minimum around x equals to 5, y equals to -5. So we can see that visually here. And so it's a nice example to work with. And if you want to have a look at the macro in LibreOffice, we can have a look at it using macros, edit macros. And then it's actually saved within our ODS. If we just double click on this module 1, we can see that we have a very simple function that is evaluated here. If you don't want to use that macro, you can simply copy this equation into that fxy box here, and it should work exactly the same. This is just showing you that we can actually run these workflows using macros in the spreadsheets as well. Okay, so that's it. Of course, just to demonstrate, if we do update those xy values, we get a new fxy here. And then if we copy those values here into these optimization history iterations, we should be able to see that the plots on the right update. So if I just fill that in here, we can see, yep, we've got a movement of these line plots here. And we'll actually be updating this input here automatically within our optimization through the web app in a minute. So let's go there. Okay, so this is our web app, the way it looks like when you open it. You've got a few options here that allow us to open and save work sessions. But for here, we're just going to create the simple workflow from scratch. So let's right click, add an empty node, and we can edit this by clicking on it. We're just going to call this paraboloid. There we go. And choose the LibreOffice comp latest API. So once we've selected that, we have this option to upload additional files. These are Python files, Python scripts that act as wrappers around our spreadsheet. I won't go into detail into these just now, but they are fairly standardized, and they allow you to add and modify the the interaction with the spreadsheet. So add, for example, additional macros and so on as you need. So at the moment, we're just going to upload our simple setup here. Yep, this is LibreOffice setup, our compute function. And we don't need any requirements here because we don't have any additional Python library requirements. In this case, we only have one component other than the driver in our flow. So this is going to be both the end and start node. And then we're going to add some, let's just save this. And we're going to add some parameters to this as well. So let's start by uploading our paraboloid spreadsheet. So this is one of our parameters. This is actually a user input file parameter. And parameters are simply values and data that is set outside of the Python scripts that we've just uploaded on the properties tab, and allows us to, for example, set our input and output values initially. So here in this example, we're going to have 4 different additional parameters other than our input files. I'll just copy in here. So X, Y values, this is arbitrary values to start off with. This is initialized to just a random number. And our ODS file needs to point to our ODS file that we've just uploaded. Okay, so let's save that again, and we can move on to the inputs. So the inputs are the same as our X and Y that we've just set. And so if I just click outside, this formats it. And if I just copy my fxy in there as an output, so you need to make sure that there's no trailing commas, otherwise the JSON isn't valid. So if I lift this in, I'd get an error message down here. So I need to make sure that that's not in there. And that's it. So we've set our outputs, our inputs, our parameters, and we've uploaded our different API files. The log at the moment is empty, so this will fill in as the component executes, and we'll also have access to actually download the file snapshots during or at the end of the run. So we can save this. Now to automate the execution of this, we actually want to add a driver to our workflow. If we just executed it as is, we would just run the paraboloid spreadsheet once with the arbitrary inputs that we've set. But to make this more interesting, we want to add an optimization driver. So here we want to use OpenMDAO to minimize the paraboloid function. So we'd want to try and find the X and Y values that minimize our fxy output. And we know that there's a known analytical solution to that. So it's a nice example to work with. So here we just start again. We call this OpenMDAO. There we go. We now select the driver API. This is now a driver component, and we also need to select appropriate setup and compute functions. In this case, we do need to set the requirements because we do need access to, I believe, SciPy and OpenMDAO, NumPy as well, and matplotlib if we want to use the plotting functions. And that's it for the properties. In terms of the parameters, I'm just going to copy in some parameters that I will explain. Right, so this is a bit more complicated than our paraboloid. So we're setting a lot of standard OpenMDAO input properties here. I'm not going to go into detail into all of this. The main thing is that we're using an SLSQP optimizer, which is a gradient-based optimizer. In this case, we're not actually feeding any gradients to this algorithm, so we'll be using finite differencing on the paraboloid to calculate those. Obviously, this is completely up to you what you want to use. This is just an example. So in terms of the inputs, we set here that our inputs are x and y for the paraboloid component. There's some upper and lower limits set as well. And then the output is our paraboloid fxy function. And that's our objective. So we're trying to minimize that, basically. That's what this is saying. We're also outputting an N2 diagram, which is a sort of flow diagram for optimization, and a plot history. So this is a history of the iterations of our optimization. Okay, so we've set this, and then now the final thing is that we do need to add a user input file. So here we're uploading a the open MDAO OM component. So this is a standard explicit component which you can which is based on the OpenMDAO implementation and the examples online. So once we have uploaded this, we I think are ready to go. So we don't need any inputs and outputs here. And again, the log is empty at the moment. So we'll save this, and now we'll click start. So this is going to take a few minutes to just get running because we're actually launching this in the cloud. So I'll see you when this is going ahead. Okay, so this is just starting to execute now. So we can see that both the OpenMDAO and the paraboloid components are running. And we can see that it's iterating through the paraboloid fairly quickly. And it should be completing now. Okay. So this should be finished. Let's just refresh the page. Okay. So we get the message that our run completed successfully. Okay. So so we can see the number of iterations and the time of the last event here. And they both pretty much finished at the same time. Now we can have a look at our paraboloid output here. So this will be under our log. And that will download our zip file here with our outputs. So if we open that, you can see we've got our input folder and output folder. And the inputs, we've simply got the files that we've uploaded earlier. And the output will have our paraboloid output spreadsheet. So if we open that, enable macros, then we can see here that we've actually got something plotted on our plots here on the right, and the optimization history has been filled in. We end up with a value which is very close to the analytical minimum of this paraboloid function. So that's x equals to 6.666 and y equals to minus 7.333. And it's got a minimum value of around minus 27 for fxy. So this looks like what we expect to see. And we can now also have a look at our OpenMDAO component. Yes, I should just say this is obviously plotting all the executions of our paraboloid, including the function evaluations that contribute to the finite differencing for the gradient calculation. So this is why this looks a little bit unsmooth. But if we just close this down again, so we know that we had 13 iterations of our paraboloid component. So that's shown here. If we now go into our OpenMDAO output, we can do the same thing, download that, and look at our outputs here. So as I said before, we've got this N2 diagram, which is a standard HTML file. And it just shows our paraboloid component here, which has two inputs, so our x and y, and it has a single function that we're optimizing. So not a very interesting diagram, but obviously if you end up with a lot of different components in your workflow, visualizing this in this way can be quite useful. If I now go back to my outputs, I can also have a look at, so these are optimization history plots. So I can have a look at how our x function changed, for example. No, this is actually just plotting the major iterations. So we don't have all the intermediary values. Now we can see that we end up at the optimum fairly quickly. So this is the same that we had in the Excel spreadsheet a second ago. And now fxy is minimized here as well. We also have a run log. So this is a summary of the OpenMDAO outputs with all the iterations listed. Right, so we've just gone through these 3 different steps. We've created and executed a spreadsheet component within the Dapta web app. We've also automated its execution within a driver, a workflow, which includes a driver. So that's an optimization component here using OpenMDAO. And we looked at the inputs and outputs that we were able to access without having to open the Python files at all. So this was a very quick overview of how to use spreadsheets in the Dapta app, and I hope you enjoyed it. Now, if you want to get started using the app, you can sign up for a free trial on our website and start testing straight away. There's a few full online tutorials available already, and we're building on this quite quickly. So have a look, and also if you've got any feedback or ideas, I'd be happy to hear from you. Thank you.